Hello everyone, Phil here. So the first video I published was quite the abstract one, therefore I decided to focus on something a bit more down to earth, a bit more concrete for this one. So I have moved the location, I'm now sitting on the floor, and today's topic is cement. The joke was awful. For real though, let's have a chat about concrete, because we have a massive problem with it, and it's one without an easy solution, or some will argue without a solution at all. Before getting to cement itself, let's have a brief chat about what makes a material successful. Now, if I ask you to name one material that you consider as such, chances are you'd either come up with something very high-tech and exotic, maybe carbon fiber or graphene sheets, just talking about carbon right now, wonder why, which enables the progress of the few thanks to its very avant-garde nature, or maybe something very common and mundane, such as, I don't know, steel or asphalt, which fuels the progress of the masses by the virtue of its simplicity and accessibility. Now, of this second group of materials, I would argue that there are few as successful and widespread as the good old Portland cement. Since the dawn of civilization, builders have been on a hunt for something that can be used to bind together other building materials. And now the first people to use such a material on a large scale were the Romans, definitely, who used a volcanic pozzolanic mixture mined near the town of Pozzuoli. That's where the name comes from, although in Latin that would be Puteoli. And the town is in near Naples in southern Italy now, if you care about that. They weren't the first ones, though, to use such a material. Likely this title belongs to the Minoans from the island of Crete, and definitely other Greek civilizations used pozzolanic mixtures, but large scale, again, for the first time, it was the Romans. This just goes to show how much humans have kind of always needed a cheap, easy to use, reliable and widely available building material that could be used to stitch together other stuff such as bricks or cobbles. Now, while pozzolanic cements are a fascinating topic on their own, if we were to delve into those as well, this video would balloon way too much in length. So to keep things simple, let's just say that they had one critical defect. They were natural materials. Thus their quality was not very stable, not very constant from one batch to the next. And moreover, they needed to be mined from one location and transported to the final location of use, which is problematic if large quantities are needed. And, well, let me tell you, large quantities are needed. We're talking about tens or more likely hundreds of kilograms of cement to build an average house, let alone like a block of flats or something the likes. According just to some back of the envelope calculations, those are the numbers I found. I mean, this is the source I used, but you can find these estimates all over the place. Just look for them on the internet. I don't know jack about building houses, so I just trusting professionals here. But again, you can find similar estimates all over the place, really. Everything changed on the 21st of October, 1824, when a chap named Joseph Aspdin, I don't know if I'm pronouncing it correctly, he was a bricklayer from Leeds, England, received approval for patent number BP5022, titled An Improvement in the Modes of Producing an Artificial Stone. This is all just a fancy way to say that he first patented Portland cement, or what is today commonly referred to just as cement by the general public. It is worth noting that this was not very similar in origin to the Portland cement that we use now today, and that since the patent expired, a lot of manufacturers rushed to refine the formula, while state regulatory bodies all around the world churned out ever more precise definitions of what a Portland cement must contain to be considered as such. So what makes Portland cement so special? Well, the short answer is that it consists of two of the most widespread materials in the world, i.e. limestone and clay, cooked in relatively basic ovens at very high temperatures for a few hours, which will produce something like this. Then you mix that with water, with something like this, not sponsored unfortunately, and hey presto, you made a reliable and efficient building material for pretty much 4 pennies. And the patent on it expired like more than a century ago, so you're even going royalty free. Great! I imagine that you're a builder in a developing country with a booming economy. In case you are, actually easier, you don't have to imagine. You can now understand how such a mundane and basic material can be actually very cool and very useful. So cool in fact that humanity used a lot of it since its inception, and it kind of keeps on doing that. And that is kind of a problem, considering the enormous amount of carbon dioxide produced by its manufacturing process. Oh yeah, we're talking carbon emissions again! So how's the world doing? Well, in a nutshell, not great. And how is the world doing in this regard of cement production? Also not great. In this graph you can see how one country accounts for pretty much more than half of all cement produced by mankind. And no prizes for guessing which country it is. It's, wait, France? No, just joking. It's China, what do you expect? And I mean, it's not hard to figure out why. China's economy has been expanding at an amazing rate, and its infrastructures have been building up like crazy. It is a very appropriate words indeed for the context. I don't know, I'm not an economist, whatever. But the point is, if you need to build a lot of stuff, like houses and skyscrapers and roads, bridges, dams, and things like that, well, a lot of cement will be needed. So let's take out China from the graph for a moment, for the sake of seeing what the other countries are doing. Next in line is India, here, which also has increased its production quite dramatically in the last couple of years. Developed countries instead usually have either a slowly increasing or more often a slowly decreasing production, which kind of reflects the largely already developed infrastructure of these countries. As you can see here again from a bunch of developed countries, most of what they're doing to their infrastructure is maintenance more than building more. And maintenance is a bit spotty also from time to time, but let's not get bogged down in that. And let's look at developing countries instead, which instead kind of have a similar production to India and China in pattern, although the amounts produced are usually much smaller. Sometimes a bit more irregular, like look at Indonesia here, or look at Vietnam. These countries have been kind of increasing their cement production in the last few years. Now the data set is from 2000 to 2014, because that's the first one I found, and that's fine enough so that we don't get too recent with the data, which is never the best idea if you can avoid. So can we extrapolate how this pattern will look like in the future? Well, for sure. In fact, let's do it. Oh well, when doing predictions about future trends, there are two possible approaches. First one is to get a team of proper data scientists to work for months on the problem, making a lot of assumptions and then testing each one of those, looking at countless variables and producing a decent model that will predict how the trend will look like in the future. And this will likely end up in a peer-reviewed journal or something the likes. Second possible approach is to get a random bloke on the internet that has got some idea on how to manipulate data, and will do that for free, with freely available data, and that would probably end up in a YouTube video and not much else. That's probably not good enough for anything else. And guess which approach we are going for today? So first, the quickest but also sloppiest thing we can do is, let's take a time interval, again 2000 to 2014, because the first reliable dataset that I found was comprised between those two numbers, so that's what you get really. And again, using too recent data sometimes it's not the best idea. Let's just assume that cement production is tied only to the world's population. Take the world population in 2014, which is 7.254 billion, according to the World Bank. Get the most accepted prediction for the world population level off number, which according to the same source is around 11 billion people. That will be in 2100, but it doesn't really matter the year. And do a simple proportion, like this. Add errors based on population growth models. Let's just use the 2 sigma interval, which is this one you see here. Here you go, your prediction is ready. In 2100 we will be producing between 5,765 and 6,919 million tons of cement. And this is not so bad actually, doesn't even double, right? Now, we know that up to 50% of CO2 emitted in order to make cement comes just from the heating of the ovens. So if we manage to completely switch that process to renewables, we'd actually be emitting far less than we are emitting today. Great, again. Is this accurate, though, as a prediction? Because I'd argue not really. Of course, I'm asking a question. I know it's not accurate. As we have discussed earlier, most of the increment in global cement production recently came from developing countries. But our model, let's say, assumes that all 7.25 billion people alive in 2014 lived in developed countries, which is very far from the truth. Therefore, the predictions we just made is a very optimistic one. Let's go for a slightly less rough approach, just for fun, and produce something a bit more reliable as a prediction. Still rough, still back of the envelope, but a bit more reliable. Let's have some fun again. So do we actually have fun doing this? We're going to build a new prediction on one big assumption. We're going to assume that a developing country of size X and population Y will increase its cement production at the same rate as two developing countries of size X.5 and population Y.5. So these two variables are tied linearly. In practical terms, just to make an example, let's take three developing countries called A, B, and C. Let's say that A is as big and populous as B and C combined, and their population and economy grow at the same rate. Under our assumption, therefore, their cement production will grow in the same way. This assumption I'm making in order to apply the increment in cement production from a country like China and partially like India to countries that have yet to experience the bulk of their development. It's quite the big assumption, again, but hey, that's what you get to get these numbers from a random blog on the internet using approach number 2. You want better? You can pay me or somebody else or both and use approach number 1. But you won't do it, so that's what you get again. We need just a couple more data though, and one more assumption. Once again, according to the UN, we can expect the world's population to level off at around 10.9, 11 billion people by circa 2100, and also that population growth will occur overwhelmingly in developing countries. We will also take the World Bank's data about the economic development and assuming that today, or at least in 2014, circa 1.3 billion people were living in developed countries, but we will also add to those 1.3 the around 1.4 billion people that were living in China in 2014, as their population growth has almost completely leveled off and we want to apply their past rate of growth to other developing countries. So we are leaving China out of the equation just to make things a lot easier. Once again, it's quite a big assumption, but we're more seriously just looking for an estimate, not for a strictly quantitative model. Nobody's going to use these analyses for practical purposes anyways. If you're thinking about doing that though, whoever you are, stop immediately and look for real studies. Don't take data science advice from a random bloke on the internet whose credentials you have no idea about what they are. Please, seriously, don't. Just a guy having fun. Let's assume then that cement production will keep on increasing at the same rate as it has been increasing until 2014, and that this will carry on kind of in the same way until all of the human population lives in a developed country. Now, the shape of the growth might change quite dramatically based on the assumptions, but the final number should be more or less the same. At that point, we're going to assume that it will peak and then slowly start decreasing as all the recently developed economies switch from expanding their infrastructures to maintaining them. As you can see from this graph, all of these gray lines do not drift too far from the population predictions that we have used. These two dotted lines are called the 2 sigma interval, and without getting too much into the middle of it, it means that 95% of possible results are falling inside this interval. So there's a 95% chance that in 2100 there will be between 10 and 12 billion people on Earth, give or take. And of those people, we are assuming, as explained earlier, that 8.2 billion will live in a developing country between now and 2100, thus indirectly contributing to the increment in cement production. So if in 2014, with 2.8 billion people living in developed countries, or in China actually, we produced 4180 billion metric tons of cement, by this model's rationale, we are going to be producing between 14,929 and 17,914 million metric tons of cement. So we will be producing between 3.57 and 4.28 times as much. Which means that even if we switch fully to renewable energies, thus removing 50% of CO2 emissions, the outlined here in the best case scenario section of the graph, we would still be emitting at least between 1.78 and 2.14 the amount of CO2 that we are producing today. So it's not looking so great anymore compared to the prediction that we did in the beginning. And also that's the best case scenario. If we fail to switch all of the energy used to renewables, so we're looking at the worst case scenario up there. Probably we're going to be somewhere in between the two. So cement is at the same time one of the most mundane, useful and problematic materials that humanity has ever created. Portland cement, more specifically, has been used as one of the main driving forces behind the increased standard of living that we are currently enjoying in developed countries. And it will likely cover the same role for countries that are developing right now. Nevertheless, its production has a massive impact on CO2 global emissions, and furthermore, the necessity for this material to be cheap and locally produced without the use of advanced equipment greatly hinders the possibility to reduce its environmental impact. As stated at the start of the video, then, we are facing a big problem without a simple solution. And maybe that's why it's way less talked about compared to, for example, energy production or personal transportation or cattle farming and so on and so on.
What's the deal with that 50% of CO2?
I beg your pardon? Why is our most optimistic goal to reduce the CO2 emissions from cement production by 50%? Why not 100%? Great question! The answer is fascinating. Unfortunately, that's a whole different topic. Someone should make a video about it. If only I knew some sort of material scientist with an interest in data and a newfound video making hobby. Wait though, I know that person. It's me! This joke is dumb. Well, I guess I found myself another topic for another video. Yay! Until next time, have a good one, people. Feel out. Thank you once again for watching until the end. These are the main sources used in the research for this video. And if you have any questions, please pop them in the comments and let's have a discussion.